Pluto is 3.7 billion miles away, colder than any place should reasonably be. And according to the basic physics of its own atmosphere, it shouldn't be this cold. Something out there is actively working against the laws of thermodynamics as we understand them, and James Webb Space Telescope just caught it in the act. Here's the part that should stop you immediately. Astronomers had a model for exactly how warm Pluto's thin atmosphere should be, based on the sunlight it receives and the composition of its gases. The real Pluto came back roughly 30 degrees colder than that model predicted. For decades, nobody could fully explain the gap. Now they can, and the answer is stranger than the mystery itself. This is the story of what Webb actually found when it turned its infrared eye toward the edge of our solar system. I'm your host, and this is the channel that chases down the discoveries other channels rush past. If that's what you're here for, subscribe, because there's a lot more of this coming. Let's start with the mystery itself, because you need to understand exactly how strange Pluto's temperature problem really is. When NASA's New Horizons spacecraft flew past Pluto in July of 2015, it delivered humanity's first close-up look at a world that had spent nearly a century as a barely resolved dot in even our best telescopes. What it revealed stunned planetary scientists. Not a dead, featureless ice ball, but a complex, active world with towering water ice mountains, vast plains of frozen nitrogen, and, critically for this story, a real, if extremely thin, atmosphere made mostly of nitrogen, laced with methane and carbon monoxide. That atmosphere came with a puzzle attached almost immediately. Based on straightforward physics, how much sunlight Pluto receives at its distance and how that energy should heat gases in its atmosphere, scientists calculated an expected temperature. The atmosphere Pluto actually has runs roughly 30 degrees colder than that calculation predicted. That's not a rounding error. That's a real, unexplained energy deficit, as if something out there were actively pulling heat out of the system that basic physics says should be there. For years, the leading suspect was haze, a layer of extremely fine particles suspended in Pluto's thin atmosphere, formed when sunlight breaks apart methane molecules, and the fragments recombine into complex hydrocarbon particles that eventually drift downward, coating the surface. Scientists suspected this haze might somehow be responsible for the missing heat, but confirming exactly how required a telescope sensitive enough to track subtle temperature changes in an atmosphere this faint, from a body this small, this far away. That's where Webb came in. Between 2022 and 2023, astronomers used James Webb Space Telescope to observe Pluto's atmosphere over the course of roughly a week, watching how its thermal signature changed as the dwarf planet rotated. What they found confirmed an idea researchers had floated years earlier, one so counterintuitive at the time that scientists reportedly described it as a crazy idea worth testing rather than a serious prediction. The haze particles in Pluto's atmosphere, it turns out, aren't just a passive layer sitting there. They're actively regulating the atmosphere's entire energy balance, heating up rapidly during Pluto's brief day, and then radiating that heat away just as efficiently once night falls. This heating and cooling cycle happens fast enough and efficiently enough that it explains the missing 30 degrees almost precisely. The haze isn't a side effect of Pluto's cold atmosphere. It's the mechanism actively keeping the atmosphere colder than basic physics alone would predict. According to the researchers who confirmed this with Webb's data, this makes Pluto's atmosphere fundamentally different from every other atmosphere in our solar system. Nowhere else, not on Earth, not on Mars, not on Titan, not on any of the giant planets, does a haze layer function as the primary thermostat controlling the entire atmosphere's temperature. Pluto, sitting at the very edge of what we consider our solar system, is running on a completely unique atmospheric physics nobody had directly confirmed until Webb's infrared instruments caught it happening in real time. And that wasn't the only strange thing Webb's observations turned up. Pluto's surface, it turns out, isn't a frozen, unchanging relic either. Webb's data revealed evidence of seasonal cycles, volatile ices like nitrogen and methane, sublimating away from certain regions of Pluto's surface as it slowly orbits the Sun over its 248-year year, then recondensing elsewhere as the seasons shift. Different regions of Pluto's surface are essentially breathing in and out on a multi-decade cycle, exchanging ice with the thin atmosphere above them as sunlight angles change across the dwarf planet's slow, tilted orbit. Perhaps strangest of all, Webb's observations added detail to something New Horizons had only hinted at, material actually being pulled directly from Pluto's atmosphere onto its largest moon, Charon. Pluto and Charon are unusually close in size and mass compared to most planet-moon pairs in the solar system, orbiting a shared center of gravity that sits outside Pluto itself, more like a double-world system than a simple planet and satellite pair. That closeness appears to allow some of the volatile gases escaping Pluto's thin atmosphere to physically migrate across space and settle onto Charon's surface, contributing to the reddish coloring scientists have observed at Charon's poles. Nowhere else in our solar system does one world's atmosphere directly feed material onto a neighboring body quite like this. More recently, Webb's sharpest published image of Pluto to date brought all of this together visually, resolving detail on Pluto's surface with a clarity that lets scientists match specific features: the pale, heart-shaped region called Tombaugh Regio, and the darker, shadowy expanse known as Cthulhu Macula, against the thermal and atmospheric data Webb had already gathered. NASA planetary geologist Dr. Raj Patel described the value of Webb's infrared sensitivity plainly, noting that it gives scientists a powerful tool for analyzing surface ices like nitrogen, methane, and carbon monoxide directly, and that the new information may point towards seasonal cycles at Pluto, or possibly even cryovolcanic activity, ice volcanoes, driven not by molten rock, but by pressurized slush of water and volatile compounds beneath Pluto's frozen crust. So here's where that leaves the shouldn't be possible part of this story. And it's worth being precise about it. There was never anything physically stopping Webb from observing Pluto. It sits well within our own solar system, far closer than the ancient galaxies Webb routinely photographs at the edge of the observable universe. What genuinely shouldn't be possible, by the simple physics scientists have relied on for decades, is an atmosphere this thin staying this cold without some active mechanism working to keep it that way. Webb didn't just take a nice picture of a distant dwarf planet. It caught directly the physical process responsible for one of the strangest temperature anomalies in the solar system, a haze layer functioning as an active thermostat, unlike anything confirmed on any other world we've ever studied up close. If this is the kind of story you come here for, subscribe and turn on notifications, because there's a lot more of the solar system's strange corners we haven't finished exploring. Drop a comment telling me which part of this surprised you the most, and share this with someone who still thinks Pluto is just a boring frozen rock at the edge of everything, because it turns out its atmosphere is quietly breaking rules no other world in our solar system breaks.